Now, in order to proceed from here, let me actually write this time discrete ODE. For purposes of argument, let me write it at time tn plus 1. Right? So this, of course, is the time discretized ODE at tn, right? Because everything is at n. Okay? Let me now write this at time tn plus 1. Right? So at tn plus 1, that becomes, in canonical form, it becomes m v at n plus 1 plus k d at n plus 1 equals f at n plus 1. All right, all I've done is write out the ODE at two different times, okay, at two different time instants, tn and tn plus 1. All right, so this is in general what we will call the time discrete version of the ODE, and when we write it in terms of the velocity, it's a sort of canonical way of writing it. All right, now this is where we need to invoke special integration methods, right? Our integration methods are based upon what we call the it's a family of integration algorithms okay, that are sometimes called the Euler family for first order ODEs. Okay? And here's how they're posed. Supposing we're considering the following ODE. Suppose we're looking at y dot equals f of y. Okay? This is the algorithm we're looking at. So what we will say here is that the time discretized version of this, or the solution as posed by the Euler family of algorithms, is the following. Right? The algorithm then is the following. It is that y n plus 1 minus yn over delta t, okay, is equal to f at yn plus alpha. All right, this is the algorithm as defined by the Euler family. I have some explanation to do here, of course, right? So what we have is the following. This is the algorithm where delta t is simply what is called the time step. It's tn plus 1 minus tn. Okay, and this is the time step. Okay, alpha is a real number, and alpha belongs to the closed interval 0 to 1. All right. Okay, so we have this setting, and since we're talking about the Euler family here for the very first time, let me, so to speak, introduce you to the members of the Euler family. So we have the following sort of setting. For alpha equals 0, right, this is called the forward Euler method. Okay, alpha equals 1 is called backward Euler. And alpha equals half is called various things. I will tend to call it the midpoint rule. Okay, it's also sometimes called the Crank Nicholson method. Okay, so those are special members of the Euler family. Of course, as indicated back here, one can design algorithms, one can develop algorithms and use them for any value of alpha between 0 and 1. Okay, so one final step I want to take in this segment is to note that the way this can be sometimes rewritten is as simply right. This thing is sometimes rewritten as yn plus 1 equals yn plus delta t times f at yn plus alpha. Okay. Now, in order to complete this description, I need to tell you what yn plus alpha is. Okay. Yn plus alpha is constructed simply as a linear interpolation between values at alpha equals 0 and alpha equals 1. Okay, and that tells you that you construct it as yn plus 1, right? Let me see, alpha times yn plus 1 plus 1 minus alpha times yn. Okay, all right. So really, when you sit back and look at these Euler family of at this Euler family of algorithms, what it is doing is to approximate our time derivative, right? So we approximate the time derivative over as a linear as a linearly varying quantity over every time interval, right? Right? Instead of saying y dot, we're just saying, well, let me just take a linear approximation of it over the time step, right, or over the time interval. So this is our approximation for the time derivative, right? And by saying that we are requiring it to be equal to f at n plus alpha, this is where the design of our algorithm also comes in over the various possibilities in the Euler family, because if we are trying to go from Tn to Tn plus 1, right? We're saying that the rate in the average rate across between Tn and Tn plus 1 depends upon f, and we are free to evaluate f, or we are leaving ourselves the flexibility to evaluate f at any value inside here, right? So at any point inside here. So that point is generically n plus alpha, right? T at n plus alpha. Okay, by choosing different values of alpha, including alpha equals 0 or alpha equals 1 or alpha equals half or really anything else, we get particular properties for our method, right? So this is where the approximation of the time derivative comes in. We have this side of it, which is the linear approximation, and this and here we're approximating the ODE by evaluating the right hand side at some Tn plus alpha. Okay. So this is the basis of the Euler method, and we are going to apply it to our time discretized ODE when we return in the next segment.